Hello everyone. Today we'll see a couple of methods to determine whether a classifier is doing good or not. Okay, so we have seen classification trees. We have also studied k-nearest neighbor method for classification. But given a particular situation, you have to choose one algorithm. So you have to decide, okay, whether you are going for KNN or whether you are going for a tree. Not just tree, do you want to go for bagging or do you want to go for random forest and something like that. Okay, so things like that we need to decide. So for that we need a method which can compare error in the case of classification. In the case of regression setup, things are simple. You can simply compute test error and compare it. But in the classification setup, should we just go for accuracy in prediction or should we worry about some other parameter? That becomes a question. Okay, so accuracy would simply be 1 minus misclassification probability, right? So it would simply be 1 minus misclassification probability. So is it a reliable estimate? Is it a reliable indicator for the goodness in some sense of the classifier? So let us say that someone tells you a particular classifier is 95% accurate. What does it mean? That in 95% of the cases the prediction given by that classifier is correct. Then what do you think? Is the classifier good? Yes, of course you think that the classifier is quite good. So what can be done? So the classifier is 95% accurate. What does it mean? That if I have say 1000 observation, out of these 1000, for 950 the class has been predicted correctly. Okay. Now let me go deeper and see the division. Okay. So this is predicted class 1, predicted class 2, actual class 1, actual class 2. Suppose I have 950 observations here, I have 50 observations here, I have 0 here and 0 here. So what does this mean? It means that yes, overall there were 950 observations who were actually in class 1, 50 observations who were actually in class 2. But what I am doing is I am predicting everyone to be in class 1 and I am predicting no one to be in class 2. Okay. So my prediction rule is actually very simple. I don't have a complicated rule. I don't have a complicated algorithm. I am just saying whoever comes, classify that into class 1. And still what is happening, that of course because my class 1 was very dominant, I am still getting 95% accuracy even with such a dumb rule. Putting everyone in class 1. This is really a dumb rule. But still I am getting 95% accuracy. Okay. Why? Because the class sizes are unequal. Hence, accuracy as a measure of performance has serious limitations, especially when you have unequal or what they call as unbalanced class sizes. Okay, so what do we do? So there are multiple ways of handling unbalanced class sizes. Some people do what is known as upsampling or downsampling. What is upsampling or downsampling? Upsampling is you just repeat some rows randomly. Repeat some rows from the minority class randomly. As a result, the number of observations in minority class increases. Downsampling is reverse of that. So you delete some of the rows from the majority class randomly. So you have roughly equal classes, roughly equal class sizes. Of course, some algorithms need this because then only they perform good. Means if the class sizes are roughly equal, then only the performance is good. But here we are not talking just about performance. We are talking about measuring the performance. So we have just shown that accuracy actually is a terrible measure if you have unequal class sizes. So are there any other alternatives? So then people thought of two measures called as sensitivity and specificity. Okay, sensitivity and specificity. So what does sensitivity measure? Sensitivity kind of measures how sensitive your test is. How sensitive your test is means, if suppose you are trying to detect a disease via a particular diagnostic test, then if your test is very sensitive, then it should be able to detect even a small presence of microorganisms. Okay, so that is what is known as sensitive test. So sensitive test means it should give you positive prediction even when there is a slight indication of positive thing. Okay, so basically sensitivity is probability of getting a positive prediction when it is actually positive. Probability of getting a positive prediction in a positive class or in a positive observation. Okay, so basically it is conditional probability of test being positive. If I talk in medical terms, it is conditional probability of test being positive given that the person actually has the disease. Okay, so it would be conditional probability means it would be ratio of positive intersection D upon probability of D. Okay, so sensitivity is this. This means what? So it is number of if you don't want to write in terms of probability, it would be number of true positives, right? Because positive having disease means true positives upon total number of disease means total positives. So total positive means true positives plus false negatives, right? False negatives means actually they are positive but they have been falsely considered as negative. Okay, so this is the formula for sensitivity. Number of true positives upon number of true positives plus number of false negatives, because you need total positives in the denominator, actual positives. Okay, so actual people who have disease. Similarly, specificity is exactly a dual of this. So specificity is how specific your test is. Means if you don't have a disease, it should actually say you don't have a disease without getting confused. Okay, it should be very specific. It shouldn't confuse any other microorganisms with the microorganisms that you are testing. Okay, so it is probability of getting a correct negative result. Okay, correct negative result means what? It is probability of getting a negative result when the disease is actually absent. Okay, so this is probability of negative intersection D complement upon probability of D complement. So it is number of true negatives upon number of true negatives plus number of false positives. Why false positive? Because false positives are actually negatives. Okay, so these are two measures, sensitivity and specificity, which are generally thought of as better indicators of the performance of the classifier than simply accuracy because of this result, because of such problems that accuracy poses. For example, if I compute sensitivity and specificity in this scenario, what is it? So let us first check what are true positives and true negatives and false positives and false negatives here. So let us suppose that this is a positive class. Positive means kind of having a disease. So the other becomes negative class. So true positives are these. So true positives are 950. True negatives are here 0. Now these are actually negative but have been predicted as positive. So they are false positives. And these are actually positives but have been predicted as negative. So false negatives. Okay. So my sensitivity is number of true positives upon total positives. So total positives. So true positives upon total positives. So here it is 950 upon 950. So it is 1. Sensitivity is 1. And now what about specificity? So specificity is number of true negatives. So true negatives upon total negatives. So true negatives is actually 0 upon total negatives is 50. So specificity is 0. See, that's why this is a bad classifier. Sensitivity is good, no doubt, but there is no specificity. And in fact, this is exactly what happens when you do arbitrary predictions. Your sensitivity would be perfect, specificity would be very bad. Or reverse, means if you suppose predict everyone to a negative class, then your specificity would be perfect but sensitivity would be 0. So what you need is a balance between two. It is exactly like type 1 error and type 2 error in our testing of hypothesis scenario. So you need to balance type 1 error and type 2 error. Similarly, here you need to balance sensitivity and specificity. Ideally, we need both of them to be high, but that cannot be the case. So people draw different types of curves. So let me draw one curve. So you have 1 minus specificity on x-axis and sensitivity on y-axis. So of course you need sensitivity and specificity both to be high. So 1 minus specificity should be low. So ideally your classifier should be somewhere here. So suppose this is 1, this is 0 and this is 1. Okay, so ideally your point should be somewhere near here, means sensitivity as well as specificity both are 1. So it should be such type of graph. Okay, means, so even if you see, what does this mean? What does this thing mean? So even if I change specificity, my sensitivity ideally should still remain at high level. Similarly, even if I change my sensitivity, my specificity should still remain at higher level. So 1 minus specificity should always remain at low level. Okay, this is the graph of an ideal classifier. What do you mean by changing sensitivity and specificity? See, instead of 5% cutoff, if you use 10% cutoff, then you are going to change sensitivity as well as specificity. Instead of 10%, if you go for 1%, you are still going to get a different result. So an ideal classifier should have this. Of course, this is a random classifier. By the way, I am talking everything in binary setup. If you have more than 2 classes, things are pretty complicated. So if you have random classifier, means if you toss a coin and decide whether it's class 1 or class 2, you should get something like this, a straight line going through x equal to y. So anything above this straight line is good. Anything below this straight line is bad. You might as well randomly predict. Okay. So ideally your classifier should be, if it's not perfect like this, in most of the cases it isn't, it should be something like this. So it should go closer and closer to the actual curve. Is it okay? So this is sensitivity and specificity. So while evaluating performance of a classifier, don't rely just on the misclassification table or just on the accuracy, because this is how you can end up in a completely, you can end up choosing completely bad predictor or bad classifier. Okay, this type of curve of sensitivity versus 1 minus specificity
is known as receiver operating characteristic curve.
Okay, so ROC curve. And ideally, as I said, this is the ideal scenario. So if you consider this as a curve, area under that curve is almost 1. So area under curve, it is, if it is almost 1, then that means the classifier is good. And if AUC becomes roughly 50%, then we will say that the classifier is bad, because the random classifier has AUC of 50%. It has actually covered half portion of the rectangle. Okay, so anything above 50 is good. Of course, anything close to 1 is very good. This is sensitivity and specificity. Now, sometimes even sensitivity and specificity can be misleading. How? Again, especially when you have very unbalanced classes. Consider COVID data. Okay, so currently, how many Indians have been tested positive for COVID? Roughly 50 lakh, 51 lakh. What is our population? 130 crore. So currently we don't even have 1% positive. Okay. So just for the sake of simplicity, let us assume that the prevalence is 1%. Okay. So prevalence is 1%, means what? That out of every 100 people, suppose 1 gets the disease. So 99% of the people are healthy. Okay. So if I try to write that in the form of a table, so disease complement, test positive, test negative. So disease is 1%, so 0.01. Disease complement is 99%, so 0.99. Okay. Now let us assume that my test, the antigen test or whatever test we are conducting, it has sensitivity of 0.9, so 90% sensitive, and it has specificity also of 0.9. Okay, sensitivity and specificity both are 0.9. What does it mean? It means probability of true positive upon probability of true positive plus false negatives. This is 0.9. Okay, so probability of true positive means positive intersected with D, and we know this total probability is 0.01, right? Total positive, so it is 0.9. So what do I mean by this? So probability of positive intersected with D is 0.9 into 0.01. So what is this number? This number would be 900, so 0.009. Okay, so this number is 0.009. By subtraction, this number has to be 0.001. Okay, so my sensitivity is 0.9, tells me something about these two numbers, this number as well as this number. Now I also have specificity to be 0.9. So specificity is probability of true negative upon probability of true negative plus probability of false positive. So that is kind of like total negative. So this also we are assuming is 0.9. So probability of true negative would be 0.9 into probability of actual negative. Actual negative is 0.99. Okay, so what do I get? So I get 0.891. Okay, by the product I get 0.891. So what does it mean? So this true negative is this class. So this is 0.891. As a result, this has to be, so this number turns out to be 0.099. Correct? By subtraction, this number turns out to be 0.099. So we are saying my test has sensitivity of 0.9, specificity of 0.9. So technically it's a good test. 90% sensitivity, 90% specificity. Now suppose you go to the hospital tomorrow and you test whether you are positive. Okay, and unfortunately the result turns out to be positive. What does it mean? So now you have test to be positive, but you want to see, do you really have a disease? So you want to compute probability of disease given that you are positive. Okay, remember these things are different. So probability of being positive given that you have a disease was 90%, 0.9. Similarly, probability of being negative given that you don't have the disease was 90%. But now suppose unfortunately your test has turned out to be positive. So you want to check if you really have the disease. So probability of disease given that you are positive becomes probability of disease intersected with positive divided by probability of positive. Okay, we are just using conditional probability, nothing else. So probability of disease intersected with positive is 0.009 and probability of just disease is, probability of just positive is addition of these two numbers. Addition of these two numbers would be 0.108. Okay, so 0.009 upon 0.108. So 0.009 upon 0.108. What does it mean? It means 9 upon 108. So it is 1 by 12. Okay, 1 by 12 means how much? So roughly 8 point something. Roughly 8.33%. Okay, so probability of you having the disease even though you are positive is just 8.33%. So this is known as positive predictive power. Okay, positive prediction power or positive predictive ability. Can you see? I mean, I understand these results are counterintuitive. It's confusing. But do remember that this is a fact. Okay? Check the calculation. See if you can find any mistake. I'm sure you won't be able to. Of course, there can be some minor mistake, but no mistake in this. It is actually such a small number. Okay? Why? Because the prevalence of the disease is low, and compared to that, sensitivity and specificity of the test is not that great. So ideally you need a test which is 98% or 99% sensitive and specific to get desirable results. Okay? So this is just about sensitivity, specificity, but we were talking about how to determine performance of a classifier. So as I said, sensitivity, specificity and area under ROC curve is actually a good way to go. Is it okay? So let me stop here, go through this example again, try to mark things, and we will continue in the next lecture. Thank you.